we're going to be dumping some of these slides, okay, just FYI, because they're focused kind of on film, screen, radiography. But we went through this, we went through the anatomy on this slide. So we'll go to this next one, right here. Okay, so when you're looking at the guts, for lack of better words, when you're looking at the guts, we really can't see much difference in here because there's not much subject contrast. Do you remember what subject contrast is? It's the way that the subject attenuates the X-ray beam. In other words, we have high subject contrast between the spine and the soft tissue. But amongst the soft tissue, we don't have as high a subject contrast. And it's because the density and the tissue atomic numbers are too similar, so we can't tell them apart. So that's why we would have like this barium enema here. This is a double contrast barium enema, and all of a sudden we have a high contrast here between the bowel and the other soft tissue. Yeah?
What does double contrast mean?
Double contrast, good question. Double contrast is, see the air here that's darker? Okay, so they pump them, they pour in some barium, that's the white, and then they fill them up with air. You have a little bulb, like a blood pressure cuff, and you just pump them up. And then you roll them around on the table. Yeah. And so imagine having your stomach so full, and then you have to roll around on this hard table and not bear down. And so, did I tell you what my goal was with every barium enema I ever did? My goal was to have the patient thank me after the procedure was finished. Why? If you can get a patient to thank you for giving them a barium enema, they'll thank you for anything, right? And what I did was I learned this from a tech that I just respect so much, and he taught me when I was a student, and I've just gone on with it. Imagine being the patient going in. I don't know, maybe some of you have had to go in. It's a miserable procedure. Do you think the patient says, all right, I get to go in for a barium enema? No, they don't. They've been up most of the night with the prep because they're going to clean out everything. And so they're tired. Their rear ends hurt because they've been wiping, right? And then they are going to go to the hospital, and some stranger is going to put an enema tip in them and do this procedure. Yeah, they're not real happy usually. Mm-hmm. So I used to tell them, you know what? You're going to feel like a puffed up toad, and then we're going to roll you around on the table. And I just joke with them, This friend of mine, the tech that taught me, he's shall I say we get along really well. We have the same sick humor, okay? And I was in the room, I never used this line, and he said, in San Francisco, I would get tips for this. And I said, I just can't go that far. But with the contrast media in there, we have higher contrast. Now, this patient's in a specific position right now. Anybody know? Are they supine? Are they prone? Are they on their side, or are they standing up?
Prone. The other side.
I've heard prone and on their side.
I'm going to say prone as well.
You're going to go with prone? Prone is correct. You have to think about how the anatomy, okay, here's the cecum here, all right? Ileocecal valve. Actually, you can see the appendix is right there. You can see the appendix. Yeah. And then what happens is it goes to the back, comes up over the hepatic flexure, and then remember when it comes across the transverse colon, right here, that comes anterior. and then it goes back posterior, and then as you get down to the cecum, or the sigmoid colon here, this is cecum over here, then this goes forward again, and so the varium has moved forward in the bowel. So prone is correct. Here we go. Scatter radiation. Anytime you add the amount of scatter reaching the image receptor, contrast is going to decrease. Memorize that, that general statement there.
Can you say that again?
Anytime you increase the scatter reaching the image, the IR, contrast will decrease. Here again, think of it like a foggy day. Okay? You just can't see the details. The two tools that you have as a radiographer to control scatter reaching the image receptor, number one is going to be collimation. I want to collimate tight. I'm going to not produce as much scatter that way. Clean up that scatter mess with a grid. A grid does not have any effect on scatter production. It has an effect on the scatter reaching the IR. This is good stuff. And it's going to, when you have that scatter, it's going to affect the lower densities on the image. In other words, here we have the H&D curve. We have density, exposure. High exposure here. This is low density at 0, high density at 4. That's maximum. If we take a look here at A and B, A is scatter on the image. Okay, so it's darker where it's supposed to be very light. All right, and B is no scatter there. Weren't the projects fun yesterday? Yeah, it'll be fun for the rest of you tomorrow. But there's one that's a little springy figure, and I heard both the teams yesterday that had the springy figure for motion blur. I heard laughing, okay, go, because you have to flip it and run out of the room before the exposure is made. Yeah, but. And so here we have it. Here we have A is going to be higher contrast, B is lower contrast. What's the difference? This A was shot at 60 kVp at 102 mass, and B was shot at 100 kVp at like 7 mass. So what happens with scatter production, as kVp increases, you're going to have a shift away from PE interactions and a shift towards scatter interactions. And then on top of that, as the kVp increases, the scatter is going to be moving in a more forward direction. So the high kVp puts more scatter on the image. That's what causes that. What do I liken it to? Here I go again. If I'm driving my truck down the road at 60 miles an hour and I run off the road, I'm going to bounce off of a tree and go into a new direction. If I'm going 100 miles an hour and go off the road, I'm going to crash through multiple trees. Okay, the same thing happens to the X-ray photons. I don't know why I use that violent example other than that's what I see in my mind about the X-ray beam going through the patient. It's just utter chaos. It's crashing. Yeah. I'm surprised the body doesn't go, ah! Fogging. The only fogging I want you to worry about is going to be from scatter. Okay? So as far as chemical fogging, we're not going to worry about that. It has the same effect though. It's going to have an impact on those low density areas of the image. And this doesn't matter if it's digital or if it's analog. You remember what analog is, yes? Film. This slide, there's fog. See, would you say that this is low contrast or high contrast? Low contrast, yeah. That makes me want to go out fishing. You want to know what's scary out fishing? Is when we're bottom fishing, we'll be right in amongst these rocks with the boat. And there are times that we'll drift past a rock and you can touch your fishing rod to the rock.
Where is that?
And what's that?
Where is that?
I'm thinking that that's Northern California or Southern Oregon. I'm not exactly sure where that is. I didn't take that image. I pilfered it.
It's abandoned Oregon.
Oh, yeah. And in Oregon. Very good. But what's really scary when you're fishing around rocks like this is whatever the terrain is that you see above the water, you have the same terrain under the water. And so you can be in 50 feet of water. Next thing you know, bam, you're on a rock. But, forget about chemical fumes. Scatter radiation will fog it. Film exposed to heat, forget about that. Low levels of ionization, okay, that's not going to be a big deal for DR. It is for film, because think about it, where our film bin is in the dark room. If there was an X-ray room on the other side that didn't have shielding in the walls, you'd have low energy X-ray coming through and it would fog the film. Just like when you see that light pollution on your image where it was exposed to light. And then anytime developer temperature, replenishment rate, or chemical concentration, we'll hit that in a second. Put a big X in this, on this slide. We don't need to go into details about film. When they produced film, they would do high contrast film, low contrast film. They would have fast film, slow film. So, they had all kinds of different compositions, and that has an effect on it back then, but not today. Intensifying screens. Some of you get to play with a cardboard film holder tomorrow. And just FYI, you're going to be shooting at 800 mass, and the machines don't go that high. Yeah. Did you do that one?
Yeah, I held it.
So how did you do it?
You held for 8 seconds.
How long was the exposure?
8 seconds each.
Really? Wow. I hadn't shot that on the new machine. 8-second exposure.
Mm-hmm.
Yeah. So the MA was really low. In fact, it would have been 200 MA, wouldn't it? 8 seconds. Yeah. Don't worry about that slide.
Wait, which one?
This one.
Depended on? This one? Keep going. Just kidding. Not that one either.
Put an X on that slide.
All right, if these show up on my test, I'm going to be upset.
Okay. Let's see, film density, proper exposure. Big thing is, we're talking about contrast. Get rid of that slide.
Really?
Now, remember, on the H&D curve, slope determines contrast. The steeper the slope, the higher the contrast. Now, why do I tell you this? Because in digital, we do have an H&D curve still. Okay, we take a straight line, turn it into an H&D curve. If, I already said high slope, high contrast, low slope, low contrast. Okay, and don't worry about this up here. It's not that big a deal. And this is showing here, film, it's two different films, the H&D curves. A is higher contrast. You can see the slope of the diagnostic range. Remember, diagnostic range is going to be right here. Okay, and diagnostic range on this one's right here. And you can see the difference in the slopes. The steeper the slope, the higher the contrast. So A is higher contrast, B is lower contrast. Questions about that? Okay, so processing. Don't spend a bunch of time on this. Here we go. Increasing developer time, and this is film in the developer. You increase that amount of time, increase in temperature or the replenishment rate. In other words, we have a higher chemical concentration. This will increase fog. Increased fog will decrease contrast. Halloween this weekend, isn't it? Yeah. That's why I have this font. I love this font, and that's why it's in red. You know what it reminds me of? Red Rob, Red Rob, Red Rob. And how many of you have not seen The Shining?
I turned it off.
You didn't turn it off? It's a scary movie.
It's one of the scary movies. My friend psychoanalyzed it through the whole entire thing, so it wasn't as scary. Psychoanalyzed it.
So that's what happens when you watch movies with psych majors, right?
He's an English major.
English major. Yeah, but if you haven't watched it, it's got to be the 1970s version, okay, with Jack Nicholson.
There's a remake?
What's that?
I didn't know there was a remake.
Oh, there have been 2 remakes, I think.
Oh.
Yeah. Nearly as scary. But yeah, did you know that part of that movie was actually filmed at Timberline Lodge on Mount Hood? Mm-hmm. Little trivia for you there.
I think I watched it in my film class here that I took. We watched like a bunch of movies.
Uh-huh.
Yeah. I don't really like scary movies.
Oh, I love them. I love them. But what it was is the little boy and mom and dad, they went up there, the custodians for the lodge during the winter, and nobody else was there. And dad goes crazy. All work, no play makes Jack a dull boy, right? And he goes crazy and they can't get off the mountain and he's gonna kill them. And the kid's looking in the mirror and on the wall, it's written, it looks a lot like this. It says murder. Red Rob, Red Rob. Because in the mirror it would be backwards, right? Yeah. Okay. As KVP is increased, beam penetrability will increase. That means that we're going to have higher penetration. We're going to produce more scatter radiation. And anytime scatter radiation increases, what's going to happen to contrast?
Decreases.
Contrast is going to decrease. And here's a correction for my lab lecture that I did that I'll fix. Ratio increases, scatter radiation decreases, and that's scatter radiation interacting with the image receptor. Please remember, a grid has no effect on scatter production. It's just going to absorb the scatter that is produced. And the whole purpose of a grid is to increase contrast. Collimation. Now, I've got to fix this slide. This is correct, but it's backwards thinking, because I always talk about if you increase collimation, decreasing collimation, you're going to have a larger light field. Okay, so this is kind of a negative approach. Okay, as collimation decreases, scatter radiation is going to increase, and therefore contrast will decrease. Now, in your notes, what I'd recommend putting is as collimation increases, your contrast is going to increase. That's an easier way to do it. So collimation, up arrow, equals contrast, up arrow. And so remember the two tools you have collimation and you have grid. When I increase that collimation, I am decreasing the amount of scatter production because I'm using fewer photons and irradiating less tissue. Does that make sense? So we're going to kind of try to prevent a mess. I think of scatter as being a mess. I have a glass of milk in my mind when I think about that. And then gonk, you knock it over, and then you have a mess to clean up. That's what the grid is all about, is cleaning up the mess. Does anybody remember anything about filtration?
Increases, it increases, contrast decreases.
Yeah, as filtration increases,
I see what you did there, but increase KVP.
it increases the average energy of the beam. Yeah, but the purpose of it is to reduce patient dose. And because it's going to absorb the low energy photons in the primary beam. What material is the gold standard of filtration? Aluminum. Lead is a gold standard for shielding, high atomic number. Aluminum is 13, Z number of 13, so it's lower. Now, when we add filtration or increase filtration, our beam intensity is going to decrease, but the average energy is going to be higher. Remember the wildebeest on the savannah and the pride of lions? Yeah, and so the lions eat the weak ones, so you'd say the herd is stronger. That's exactly what happens here with your X-ray beam. Now, you're not going to see a change in contrast with the filtration. It's in, I don't like to say in theory, it happens, but it's not noticeable, okay? Patient considerations. Things that you have to take into consideration with contrast. Here's a perfect example. Age. Do you think that a 94-year-old grandmother, and I think of the kyphotic, osteoporotic, thin grandmother that's just as loving as can be, is she going to attenuate the beam the same way that a 25-year-old Olympic athlete would? No. And so you have to take that into consideration. Weight. The contrast project last week that had the bucket of water, as the depth of the water got deeper and deeper, what happened to contrast? It decreased. Yeah. Body habits. Are they tall and slender? Or are they short and stocky, like me? Muscle tone. That's going to play a part. So these are things that you just think of the whole time. Right here, disease processes. Remember, we have additive and we have destructive, right? Anybody remember a destructive one? Disease process? COPD, osteoporosis. How about an additive? Pneumonia. We're going to have a lecture here pretty soon. We're going to be talking about technique systems and whatnot. And I'll bring in my little book that I used to carry with me. And it's just a little one, not even as big as a cell phone. And that's where I kept all my notes. And I had a section in there, difficult words to spell. And pneumonia was in there. Yeah. So what are the distances that we talk about primarily? SID and OID. So I have a question for you. if the SID remains constant and I reduce the SOD, what happens to the OID?
Increases.
It increases. Because what we've done is we've taken, okay, image receptor here, and this is my object, SID from here. If I decrease the SOD, OID increases. Yeah. Why did I bring that up? I don't know. Just to make you think a little bit. SID, when you adjust to SID, it's exactly, let's say I decrease my SID to the image receptor, it's no different than increasing the mass. Right, because you don't have as much divergence of the beam, so you end up with more photons per unit squared. Okay, as long as when I change SID or change mass, as long as I stay in a diagnostic range, there's no effect on contrast. As soon as I push the densities into the shoulder or drop them into the toe, then an SID change will decrease contrast. So will a mass change. Is that clear? Reed's up here thinking. I can see the cogs going. Do you have a question? No? OID. How will an increase in OID affect scatter radiation reaching the image receptor? Okay. What happens here is it's going to reduce the amount of scatter reaching the image receptor. And anytime that you decrease the amount of scatter reaching the image receptor, what happens to contrast? Increases at Zachary. Now, if we'll just go back to this slide here and see what we have here. You see right here, we have photons that interact with the image receptor, and those same ones right here are they're going to miss the image receptor. We don't use OID to our advantage very often. The reason is it has an effect on detail and on distortion, which we'll be talking about. We might start on detail. No, we won't today. The other group was ahead of you a little bit. You all get me sidetracked.
We're the reason you're sidetracked. You're gonna have to roll back to that one, buddy.
Isn't it fun to have fun? Processing, okay. Anything that increases fog will decrease contrast. Did you know that the processor that you're using today in lab, or these days in lab, that was just about as big an innovation as what digital imaging is today. And the reason for that is the whole purpose of a processor was to have consistent timing. Everything runs all the same. And then it would give them consistent densities. Because what would happen is if they were hand developing, there was inconsistencies in densities because people see different. But, yeah. Fogging, it doesn't matter where the fog comes from. It will always decrease contrast. What do you know? What do you know? I'm going to stop recording.